check the timing.
Okay, so thanks for the introduction and thanks very much to the organizers for inviting me to come here. This is a very new experience for me. So, this is interaction of math and physics. Everything I've done so far has just been math. So I'm learning about the physics part of it for the first time in this conference. It's very nice and interesting to see the vast range of mathematics that comes in that has come in every one of your talks. So a bit of a disclaimer. So this is my first time in a physics related conference. This is also my first time. This is a new topic that I'm working on. So homogeneous Einstein manifolds. This is so I'm reporting partly on some joint work in progress with my collaborator Masume Zare, another woman. So it seemed overall very topical for this conference. Yeah, let me start. And so this is my first time working in this, so it's not revisiting me personally, but maybe a different approach to some of the questions in this field. So Masume was also a postdoc at Munster at the same time as I was, and we had many fruitful discussions with one of the faculty there, Christoph Bohm, who is an expert in this field, and he actually introduced us to this topic, which we have recently made some progress on. So that is something I'm reporting on. I will start extremely basic, and let's see where we go from there. So the objects I'm interested in are Riemannian manifolds. So M is a smooth manifold. This is a Riemannian metric. Yes, so usually the manifold I talk about will be closed, so compact without boundary. Keep some picture in mind. A Riemannian metric is smoothly varying inner product on each tangent space. Maybe basic example you might want to keep in mind, which is also maybe good for if you are interested in homogeneous spaces. The unit two sphere inside of R3 would be inner product it inherits from R3. Okay, and the basic, these are the objects, and the basic invariant we're interested in is curvature. So there's some pictures for motivation in dimension 2. So in dimension 2, there's only one notion of curvature, which is the Gauss curvature, which is some real valued function on the manifold. And you can have these nice pictures of what it means to have positive or zero or negative curvature at a point. See if I can draw this. Okay, so in two dimensions, without defining anything, we have some pictorial notion of what curvature is, and in higher dimensions, there's more room for moving around. The curvature is a more complicated beast, and which captures somehow the failure of second derivatives to commute. So the Riemann curvature tensor is something that takes vector four vector fields or four vectors at a point as an input and spits out a number according to this kind of formula, which I'm not defining, but perhaps many of you are familiar with, and you can think of, if not, you could think of it as some way of measuring the failure of second partial derivatives to commute. Okay. Okay, but yeah, and in 2 dimensions, this is very nice. We have pictures. In higher dimensions, you have many more directions, and this is maybe not very geometrically intuitive or helpful to think about. And so we look at maybe not the whole of this beast at once, but various pieces of it, including what is important for this talk, which is the Ricci curvature, which you get by taking a trace of that 4-0 tensor on 2 of its coordinates, 2 of its entries. Maybe I say that you got it from the curvature tensor by taking a trace. And what is nice is that this gives you something which is a symmetric 2 tensor on the manifold. So an object of the same type as the metric, that is very nice. And the map, which goes from positive definite symmetric 2 tensors to sim2, which takes a Riemannian metric and sends it to the symmetric 2 tensor, which is its Ricci curvature. This is a nice second order differential operator. Which if you choose nice coordinates on the manifold, which are, for example, if you choose harmonic coordinates in these nice harmonic coordinates, which depend on the metric, the Ricci, the entries of the Ricci curvature have this nice form. That's some lower order terms. Okay, so this is one object that we need to talk about, the Ricci curvature, and then finally also scalar curvature, which finally, by taking one more trace of the Ricci curvature, gives you finally a scalar object, which is perhaps easier to think about, but you lost a whole lot of geometric information in this. But yeah, for some things also, it's pretty good. Okay, just to be on the same page in how I think about these things. I see from the talks you all work with these, but just to be on the same page. Okay. So Einstein manifolds, we say that a Riemannian manifold M, G is Einstein if it satisfies the following equation, that the Ricci tensor is some constant multiple of the metric. Right, so right, so why are we interested in these mathematically? So one common theme in mathematics perhaps is to try and find the nicest object, then the nicest object amongst whatever category you are working with. And so one thing you might be interested in is searching for the nicest metric. And metrics of constant curvature are one natural candidate. And so you could think about I said there's various notions of curvature out there. You could think about metrics of, I didn't mention the word, but you could think of metrics of constant sectional curvature. This is one notion of nicest possible metrics. Turns out they are classified, and there's not a whole lot of them. They are depending on the sign of this constant sectional curvature. It could be, and up to quotients, they'd be the round sphere, Euclidean space, or hyperbolic space. So this is one extreme. If you impose constant sectional curvature, you get a classification, but perhaps it's rather rigid. If you ask for at the other end, where you traced out completely and looked at scalar curvature, you could also ask for metrics of constant scalar curvature. There's rather more of them around. It's an easier equation to deal with, since it's an equation in a scalar, not a tensor equation. Yeah, but that does not also impose so many restrictions on the metric. It's a rather weak condition. So this condition here, asking for constant Ricci curvature, is somehow intermediate between these two extremes. So maybe you could, one reason to be, so why are we interested from a math point of view? Is one that these are canonical metrics. They are perhaps some kind of candidate for the best metric on a manifold. Some other things, maybe some features of that equation, apart from being a tensor equation with the same number of equations as unknowns. It's also a nice partial differential equation. So Einstein metrics. A nice PDE. So if you look at harmonic coordinates, they have the nice form like so. Plus some term quadratic in the metric and its first derivatives. And maybe one last motivation. They come up in a very nice geometric way as solutions to a natural variational problem. Right. So you say you fix your smooth manifold M, and I'm going to define fancy M1 to be the set of all Riemannian metrics on M that have volume 1. Then on this set, which is the points of this set are themselves Riemannian metrics on this given manifold M. On this set, which is some kind of infinite dimensional manifold itself, there is a nice functional so-called Einstein-Hilbert functional, which sends a metric to the total scalar curvature of this metric. So this map, which I will write with fancy S, which goes from this infinite dimensional manifold, sends it. So it takes any unit volume metric in there, sends it to a real number that you get by taking the scalar curvature of this metric. And that's a function on the metric, which depends on what point you're at. So what you want to get, a number out of this, you can integrate this function all over the manifold, and that gives you a number. So yeah, this is a nice and very natural kind of functional you could look at on the space of metrics. And it turns out that I had a cartoon picture I can draw. Here is my cartoon. Yellow is better. So the XY plane in this picture is a stand-in for the set fancy M1, the set of all unit volume metrics on the manifold. And on this, on this set, there is this functional fancy S. And here is some kind of cartoon of what the graph of this function looks like. It turns out that critical points of this functional are exactly Einstein metrics, exactly unit volume Einstein metrics. So unit volume Einstein metrics on M. Okay, so that may be of the several motivations that's one a nice motivation also for studying Einstein metrics in Riemannian geometry, that they are solutions to this nice variational problem. Okay. And what are the sorts of questions that people are interested in? Maybe. Maybe before questions, I mean, a nice example to keep in mind is metrics of constant sectional curvature. So say round sphere with the round sphere metric, that is a nice Einstein compact Einstein manifold. You can ask, are there more? Does the sphere itself admit others? So kind of questions we are interested in. Existence. So pick your favorite manifold. Does it or does it not admit an Einstein metric? If it does, can you classify all of these? How many Einstein metrics does it admit? What are all the manifolds in each dimension which admit an Einstein metric? And these are also pretty difficult questions to answer. So one of the other things you can do along the way is to try and construct examples. Yeah, so I'm not an expert on Einstein metrics, this being my first foray into the subject, but there's some broad overview of what is known. In dimension 2 and 3, these are classified, and they are exactly the metrics of constant sectional curvature. Yeah, I should mention that while I drew those pictures in dimension 2 of locally what a metric of positive or zero or negative curvature looks like, this is just local. If you ask that your manifold admits a metric that has the same sign all throughout, there are some topological restrictions that come in. So the other day we saw one most beautiful theorem. I can pose my favorite beautiful theorem in mathematics is the Gauss-Bonnet theorem, which places some topological restrictions on what sort of global geometric structure a manifold can admit. There are some topological obstructions out there, including in dimension 4. While we don't have a classification, the higher dimensional version of the Gauss-Bonnet theorem, so the Chern-Gauss-Bonnet theorem in even dimensions, it turns out in dimension 4, it gives you a topological obstruction for a closed or manifold to admit an Einstein metric. Namely, what is called the Hitchin-Thorpe inequality, that you can't just have any old closed four manifold admitting an Einstein metric. There better be one which satisfies the following topological condition. That the Euler characteristic of the manifold be bigger or equal to 3/2 the signature. So this is some kind of inequality constraining the topology of such a manifold that can admit Einstein metrics. Okay. It's a necessary condition. Yes. Yeah. It's not sufficient. Yeah.
What was that notation?
3/2 times. So this is tau, the signature. So if you have a four manifold, yeah. So you have a closed four manifold, then cup product on cohomology gives you a map from H2 times H2 to R by cupping and then integrating over the manifold. So if you are in 4 dimensions, then there is something topological which gives you which out of the topological structure of the manifold, you can cook up this number. First approximation, this is what you can say, and this is how you go about it. Yeah. Without talking about cohomology. Yeah, do you have something to? Through Chern-Weil theory? I mean, But you'd have to integrate over the manifold. Yeah.
No, I just know that the signature you can also compute through Pontryagin numbers or the Waal curvature.
Ah, okay. If Pontryagin numbers helps, then it is, yeah. It is, this is the first Pontryagin number of the manifold. Okay. Okay. All right. And okay, and construction of examples has largely been through maybe explicitly approaching the PDE in the setting of Kähler manifolds, or also through various bundle constructions. And through symmetry constructions. So there are various homogeneity one and homogeneous examples. And what I want to talk about is the setting of symmetry, in particular homogeneous Einstein manifolds. So this is the focus of the rest of the talk. Okay, so the setting now, the manifold is a homogeneous space, meaning this Riemannian manifold has a transitive group of isometries, so such that there's some group which acts on the space transitively, meaning every point can be taken to every other point, and isometrically, meaning it preserves the metric. And in this case, which I guess also appeared in some of the talks yesterday, the manifold can be identified with the coset space G mod H, where H is the isotropy group or the stabilizer group of the metric at some point. Please.
Sorry, in these obstructions, there is, this is irrespective of the value of lambda, whether it's positive or negative.
Yes.
Okay, so they're just for all.
Yeah, but there's a dimension restriction. This is in dimension 4. Yeah, and it comes out of the so that there is the Chern-Gauss-Bonnet theorem also in dimension 4. All the curvature terms can be related to topological terms. So curvature terms are pointwise, but to Chern-Weil theory, you can relate them to topological invariance of the manifold. So that is what goes into the result.
And so therefore, it's whether lambda is positive or negative, it doesn't matter. This is still a necessary condition for this.
Yes.
So this condition is satisfied, you can get an Einstein metric or other way around? No. Or it is not sufficient.
That is, M admits an Einstein metric implies M must satisfy this topological condition. Other questions? Okay. Okay, so when you're in the setting of homogeneous spaces, I asked that the metric that I am seeking on the manifold be one that is invariant under this Lie group action, this transitive Lie group action. That's a pretty strong condition. So if the group action is transitive, you can take every point to every other point and it preserves the metric. So the whole geometric content is determined by the metric on one tangent space. And so in this setting, all the curvature terms, which were actually second order differential quantities in the metric, they turn into algebraic quantities. So they can actually be expressed as rational functions in the coefficients of the metric at one point. And so we say that the homogeneous space curvature quantities are rational functions of inner product on one tangent space. And so the Einstein equations in this setting become a system of algebraic equations. Yeah, now there's no dimension restriction, but there is a huge restriction in that we are looking at homogeneous manifolds and metrics invariant under this transitive group action.
Maybe I don't quite understand, but how do we suddenly jump to rational functions from this group structure? So basically this presumably coset structure that you have. Is it a coset structure or just a,
So G mod H is a coset space. Yeah.
Okay. So then how do we jump to rational functions there? I didn't quite get that.
Yeah. So I ask that the manifold itself have this transitive group action, and I ask that the metric be invariant under that. So it's a very strong condition on the metric. So you know the metric at one tangent space, then you know it everywhere else, which is of course not true for a general metric. So maybe this is one indication that the curvature quantity. So first of all, the curvature quantities would be the same at every point. And you can compute them just out of this. So all the entire geometric data is contained in the inner product at one point. So at least that is one indication that that you would have functions just of these numbers, these n choose 2 numbers. Another thing you could look at is the Koszul formula for writing down the covariant derivative. So you can write the covariant. So when you write down the covariant derivative, it has some terms that come from differentiating the metric, and it has some Lie bracket terms. So if you are working with, if you choose left invariant vector fields, so vector fields invariant under the group action to compute the covariant derivative, then the derivative of the metric is just 0. So the part in the covariant derivative that comes from differentiating the metric, that is just 0. But you still have these Lie bracket terms. Maybe this is maybe some kind of indication. Okay. 10 minutes. Okay, let me try. So the Einstein equations become a system of algebraic equations. So some rational functions in the coefficients of the metric equal to 0. And that is a significant improvement, you would think, from or a significant simplification from having to try and find solutions to this partial differential equation. But it turns out that these algebraic equations are pretty resistant to solutions. So they are surprisingly non-trivial to find examples beyond certain restricted cases. Also to prove general existence results. So I'll say that although these are algebraic equations, yet existence is non-trivial. And like this here. Yeah, okay. I can't write the equations. I don't have equations in mind, but so the example I started with, this is an example of
U1.
This is an example of this kind of a coset space. It's the round metric is invariant under this action. Yesterday we saw another example in one of the talks. We saw complex projective space. We saw complex projective space written as a coset space like this with the Fubinish 2D metric. These are some examples you can keep in mind. Thanks.
Even S3 can be seen, right? S3 3 sphere can also be seen.
Yeah. So yes, so S. With the round metric, there are other metrics out there. Yeah, we can talk about it later. Yeah, I mean for a given smooth manifold, you can have different groups acting on it transitively, and if you look at what are all the invariant metrics under that group action, depending on what the group action is, you could get different answers for the same smooth manifold. Okay, let's say that there's maybe in the study of this there was some progress by explicitly studying the algebraic equations. So maybe some existence results under certain assumptions, like some even classification results on the compact rank 1 symmetric spaces. So here's projective spaces and so on. So on them, homogeneous Einstein metrics on them are classified. And there are some other results assuming some restrictions on the rank of the group, maybe some existence results on Lie groups, assuming restrictions on the rank of the group G. So this is the summary. Some progress by studying algebraic equations. Maybe some subsequent advances use the variational approach. So nice that I have this picture over here. So this was a very fake picture when I drew it for all manifolds, for all Riemannian metrics. This the space of unit volume metrics is some kind of infinite dimensional manifold. When you're looking at homogeneous spaces, it's still maybe not two-dimensional as in this picture, but at least it becomes something finite dimensional. So you could restrict to this G invariant setting and still use the variational approach. So study how the functional also simplifies. The scalar curvature is just some constant function on the manifold now because the metric does not depend on what point you're at. And studying this functional, yielded various results. obtaining some sufficient conditions for existence. So sufficient conditions coming out of the Lie group data. So yeah, maybe I'll say a little bit more about one of those results a little later. So maybe so some works of Wang and Ziller, later of Wang and Ziller. These were maybe in the 80s and then some in the early 2000s. And then
for S2, you could just verify the statement, right? What is known, that those saddles will be exactly what is the ones of constant curvature, sectional curvature. For S2, if I'd taken the manifold to be S2.
Yeah, okay, so on S2, there is only one notion of curvature. So there's only two dimensions. So scalar, sectional, Ricci, they're all just the same thing.
That's true. I agree.
So yeah.
So we can't do this exercise to see the saddles and say that there is.
No, sorry, I'm thinking. Yeah, maybe what you said, that if you restrict to G invariant metrics of unit volume, then this whole yellow set down here is just 1 point. Okay. Yeah, but yeah, with all of this, the classification is only up to is known only up to dimension 10. Sorry, dimension 12, and there are some there are many sporadic results in higher dimensions on certain infinite families of homogeneous spaces in all dimensions, but there's not really a clear picture, on general results about existence beyond these that I have mentioned. Yeah. Oh, I have 2 minutes. Maybe I can just give you a motivating example and then just say that these are the kind of questions we are looking at. So a motivating, maybe for this new approach that I wanted to talk about, a motivating example would be this particular family of 7-dimensional manifolds that look like this. Let's see. So they are 7-dimensional manifolds that are parameterized by 2 integers. So they look like SU3 mod a circle. So this Lie group has rank 2. This is a circle sitting inside its maximal torus with a slope k, L. And as you vary k, L amongst pairs of integers, you vary k and L amongst pairs of integers, you get different 7-dimensional manifolds, even though in each case the group, so the same group G, the group H was varying amongst ones like these. But they are all just circles, but it's a different embedding of the circle as you go through the family. In fact, this family of spaces, all of them admit an Einstein metric. And even though they are all G mod H, with H being by itself the same group, there's actually infinitely many homotopy types amongst them. So in spite of this, there's a lot of topological variation. There's many different, they are different as smooth manifolds, but they all have this relation, and they all fiber over, they all actually appear as circle bundles over the same 6-dimensional manifold, which is SU3 quotient out its maximal torus. So there's a family of these spaces maybe one parameter family if you slightly expand your horizons to not just ask for integer coefficients here, but say real coefficients. So if you look at one-dimensional subgroups of this that are not necessarily closed. So if you slightly expand your horizons to that, you get a one-parameter family of spaces, some of which are not globally homogeneous spaces. They are what are called locally homogeneous. But there is a way of thinking about them all being fibered over, all being S1 bundles over the same base space. Yeah, and yeah, maybe for want of time, I can just say that what Masume and I are interested in studying, and what, yeah, we hope to put it on the archive before this conference. I could share more about it, but you know how it is. These things don't always work out. But we believe we have an existence result for this kind of setting. You have some Lie group, say this is the maximal torus, and you have a family of subtori of the same dimension. So this kind of a setup where you have a torus, so you have your manifold is the total space of some torus bundle over a base, a homogeneous torus bundle like this. And by departing from the variational approach and by studying actually studying the algebraic equations, breaking them up into equations on the fiber and base of this kind of bundle, we believe we have managed to get an existence result in this setting, which is a general existence result, not specific to G and dimension. Maybe a motivating result was one of which actually did use the variational approach. Yeah. Yeah, so by studying this, the scalar curvature functional, he associated to any homogeneous space a certain simplicial complex constructed out of the Lie algebraic data, such that the non-contractibility of the simplicial complex is a sufficient condition for existence of Einstein metrics. So this result, which I just said in words, there's some result out there, some existence result out there, which has some assumptions which are not always satisfied for all homogeneous spaces, but that served to give us some indication that there's some connection between existence of Einstein metrics on the base and this family of manifolds all fibered over the same base. Yeah. Okay, so maybe I'll stop here. Thanks for your attention.
Just to ask about your result, is it for, you've given the example of 7 dimensions, but your result is dimension independent? Or?
Yeah. So okay. This was something, existence on this particular family was proved in the 80s by one. Yeah, our result is dimension independent.
I wanted to know if the results only depends on the Lie algebras, on the infinitesimal structure, or they really depend on the group. So do you need, since
I mean, you can,
you take this, you're taking general results on Lie groups.
Yes.
Okay, but there might be different Lie groups with the same Lie algebra. So
okay.
do the results depend on the Lie algebras or really on the groups?
We asked that the group be connected.
Okay, yeah. So you're choosing the unit.
Yeah.
Any other question? Just curious that these 7-dimensional manifolds have anything to do with Joyce manifolds or G2 holonomy manifolds?
I don't think so, no. This is a family of manifolds called Alof-Wallach spaces. They were interesting for constructing new examples of positive sectional curvature, like infinitely many homotopy types, sectional curvature, yeah.
So you said that when you have, you look at this homogeneous class, before you put in the condition of it being Einstein, you already have reduced it down to finite dimension. Is that right? Is
Yes.
that what you're saying?
Yes,
I see. So then it becomes a finite dimensional variational problem.
yes, yes.
So in terms of counting the number of, so the question of enumerating the number of manifolds or solutions to, say, the Einstein equation, which is what the Einstein metric is, Einstein spaces. These would be then necessarily, finite contribution to, say, in the physics context, if you were to do Euclidean gravity, you'd want to sum over all possible manifolds. And so all of these homogeneous cases would be things which would be finite number of contributions to them. So is that right? So they would be, since it's a finite dimensional space, is it true that there's a finite number of, or a countable set of saddles? I guess that's my question. Or are there, lines of saddles or things of that sort, basins?
I don't immediately know the answer, but I believe not. I believe by work of the variational study in Baum-Zeller tells you that the functions are pretty nice, and yeah, so they are. I don't.
Countable isolated number of saddles is what we will be interested in.
Okay. I think so, but I'm not sure. Yeah.
Any other question?
Yeah. So you talked about mostly symmetries which are like homogeneous spaces you admit. So if you loosen that symmetry, some sort, so do you expect certain kinds of Einstein manifolds that will admit or some bounds on Einstein manifolds or something?
I don't know the answer. Yeah, I know that. I mean, if you slightly relax the symmetry, so even if you relax to what is called cohomogeneity 1, it's like a generalization of rotational symmetry. Even there, like existence results are very hard. It's not classified what are all such Einstein metrics of cohomogeneity 1 on S4.
Okay.
Yeah, so I think even though the equations reduced to ODEs in that setting, even there it's quite open.
Any other question? Otherwise, let's thank Anusha again.